Hello, my name is Babic, and I will present to you GestureDrawer, which is a one-handed interaction technique for user-defined imaginary interfaces. And this work was done by the BMW group together with the University of Condense and Media Interaction Lab in Austria. Our work was mainly inspired, of course, by the automotive domain, where we investigate how the human-car interaction will need to adapt in the future when we have a manual driving mode and an autonomous driving mode. There we ask questions, for example, how can we keep the driver interacting safe and eyes-free while he drives manually, where in, for example, autonomous driving in level 3, where the driver doesn't need to drive anymore, but he just monitors the cars and his automatic actions. We would like to give him more expressive input, and so that he could do a much more complex tasks. Another important aspect here is, of course, the transition between those two driving modes, where ideally, or theoretically ideally, the interaction principle would remain empty-handed and eyes-free at all time, in case that the driver needs to retake manual control over the vehicle on short notice, which can then be a matter of seconds, and then if he has like mounted devices or holding a lot of devices can be problematic. Allowing more complex interactions it seems easy if we can consider that we could have a driver that can completely focus on the graphical user interface, which would then somehow reflect his actions with graphical feedback. But allowing more complex interactions while we keep the input concept eyes-free, or let's say GUI independent, is much harder. Therefore, we revisited gestural interaction, which we already have in our vehicles, but they exist in a limited way where we can just trigger shortcuts, and those shortcuts are directly mapped to a function then, for example, where we can do this victory sign gesture to mute the audio, for example. Here we notice that to design a one-handed, completely eyes-free media interaction, we need to rethink again both the gesture interaction and the underlying user interface principle that we will use. Therefore, we revisited a great example of gestural and simultaneously also screenless or non-GUI input method, so-called imaginary interfaces. The original idea of imaginary interfaces is that there is only one global spatial layout of interface controls, and that the interface controls are not visible when you interact with them. So you always need to imagine where the control is in space. In this related work, this worked in a way that the user was always holding a 2D canvas with one of his hands, and then use the second hand to interact on this canvas. And by that, he could then point at targets, he could input stroke letters, or he could draw something and then annotate something on that drawing. What is happening here is that first the user acquires some visuospatial knowledge, and then he stores that in his short-term visuospatial memory. For example, if he has this L gesture now, he could now imagine where it's like the cross-section between his index and thumb finger, and then he thinks about that, okay, this is now my interface, and here is where I imagine my control. And of course, if the system knows that, later he can then really apply this to his interaction space, let's say, which is mapped by that gesture, and then he can use this as a button if there is a button actually. Many researchers followed that approach later. They started using, let's say, okay, let's have imaginary interfaces on the forearm, or let's have imaginary interfaces on palm marks, and how could we use that as landmarks where we can position on imaginary buttons or controls. But the downside here is obvious. We always need to use somehow both hands to do those interactions, and this is then not useful for our purpose and for many other potential use cases. And additionally, they always investigated somehow a 2D plane interaction, so the full expressiveness somehow, the 3D space around this was not really considered at that point. So what we asked later was how to follow this idea is, okay, if we have a user and he has his favorite functions, similarly, which is similar to our already existing system with shortcuts, how can we give such a user access to those controls? And how can the user then learn where those controls are if they are placed in a menu which is hovering in 3D empty space? And how can the user then select each of those controls and manipulate them also in 3 dimensions, not only to trigger them in a button form? And of course, finally, how can we bring all that together so that it's one-handed, empty-handed, completely eyes-free, and in midair? So therefore, we developed the GestureDrawer, which works as following. So GestureDrawer can be summoned or created by a so-called opening action, where we first define the starting point of a drawer by making a grasp gesture and a preferred position in 3D space. Then second, we hold on to this grasp gesture and we open it by a horizontal hand movement, let's say to the right. And when we release the grasp gesture, somehow also the end position and the length of the drawer is determined. At that point, we also acquired now an understanding where we defined this imaginary interaction space via proprioception and visuospatial means. And with this knowledge stored in our short-term memory, we can now create or somehow divide this space into the amount of our favorite controls. For example, 3 was the example before. If we will open a longer drawer or a smaller drawer, the size of each control will also scale accordingly on all 3 Cartesian axes. At this point, it's also clear for the computer where we define the action and where the computer needs to put, let's say, theoretically the controls where he's sensing the gestures on which areas. And now this imaginary interface enables us, without any feedback, to find the position of each control, and then we can perform the manipulation action, which is basically just a selection. If we move our hand to a control's position and do a short grasp gesture, but if we, on the same position of a control, grab and then start moving our hand, we can manipulate this control's parameters in 3 degrees of freedom or less. Before going to the studies, I would just like to summarize the most defining aspects of GestureDrawer now. So yeah, it's an imaginary interface. Yeah, it has no user interface as in a graphical or other way observable modality. This is today. Is this hard somehow to not think about that? Because we are used so hard, we use so many touch interfaces where the interface and the input surface are so close that they're almost the same thing. But here maybe it helps that we think as if everything would be suddenly full screen and no, let's say button sliders are there anymore. Since we use short-term memory, this is also a benefit because we don't need a user to extensively learn spatial positions by gaining long-term memory, for example, by repetitive learning or muscle memory, because this is a known risk that some users will never invest so much time into learning, and then such systems have a problem. It enables one-handed spatial imaginary interaction. This is also new. In order to do that, in order to design that, we needed to remove the most essential part of related work in imaginary interfaces. This was the spatial reference frame presented by the second hand, which was then mapping the imaginary interface to the real world and somehow orienting the interacting hand to do something. Instead, we came up with a new system of defining a reference frame, which we call the retrospective gesture, and it means that we use information about the gesture that happened in the past later for the interaction to somehow navigate or hand around it. And finally, we also allow user definition by GestureDrawer. By that, we give the user much more expressive power, and this has then a direct influence on many aspects of the interaction. In case of being a novice user, the user could open a really large drawer, making the controls bigger. If the user is more like an expert user, he can open the drawer on a smaller scale and perform, let's say, micro gestures. If we have a context, or if the user feels that his gestures are socially inappropriate or in an uncomfortable position, he can also try to adapt that in a way. And also if the context changes, if you're standing, sitting, the seats in the car turn around, whatever, we can also manage this in a way. To implement GestureDrawer, we had to do strokes through midair, and we did that with having this reserved clutch gesture as a grasp, and by adding hand motion to it, we then could generate those gesture states: recognition, continuation, termination, and meaning that we'd only need to move our hand once per action. So we only grasp once and move, or if we just have a selection, we don't even need to move our hands only once for each action, independent if this is an opening action, if it's a manipulation action. So we don't have like a high frequency of clutching gestures or somehow hand motion changes in air. This is also important from the system standpoint, because the recognition system either waits for the complete opening gesture, which is this opening movement, and this movement is also sophisticated enough that we can distinguish it from normal gesticulation that is going on. And in case that the drawer is already open, he only waits for this grasp events and on certain positions and not the rest. Once we implemented that, we focused on some fundamental questions about spatial imaginary interaction, and we investigated that in 3 user studies. That was our setup, and we conducted all 3 studies one after each other with 18 participants. We used a leap motion sensor, which was attached to the right side of the chair to track the user's hand. And we also had a big screen which we could also move around for the conditions where we have something, some visualization going on and you will see that in a minute. And we use speech synthesis to relay in instructions to participants. And we also gave the user feedback if his selection is false, or correct when he was performing the selections. Before the study, the participants also had like a play session where they played around with GestureDrawer to get familiar with it, and that lasted around 6 minutes, and then they said that they are ready to go into a first study. So in the first study, we investigated how users define the drawer and how accurately can they select a control. So what they did here is they always open the drawer, and the levels represented the amount of controls that are placed into the drawer, or how many controls they need to imagine in the drawer. And then second, they just selected one of those. So they always opened, selected, opened, selected. What we found out is that the user-defined length peaked at level 4 with average length of 30 centimeters and stopped increasing after that. We see that by that we have no significant difference in levels 4 to 6. and below that we see how the length gets increased gradually to those 30 centimeters. We argue that this peak is caused by comfort. When the number of controls start increasing, participants tended to open bigger drawers until a certain limit, until it became too uncomfortable for them to open an even bigger drawer as that. And they also tended to interact in a way that they didn't move their elbow or shoulder too much. So this was somehow really like a wall in space. Furthermore, we found out that the selection accuracy decreases when more controls are positioned into the drawer, which can also be, of course, can be seen as a consequence of the length which stopped increasing, and also we can see that it was really positive for us to see that they can actually create and accurately select items at this point when we saw the results of that, although having no feedback or no landmarks and so on. We've seen later in the post-test that we have that we really have a high accuracy range from 2 to level 4, and a low accuracy range from level 5 and 6, where we see that the difference between those levels in accuracy were not significant, while all the comparisons between those two groups were significantly different. So we really have like two ranges of accuracy here. For selection time, which was measured how long the users need to access the control and select it, we see that up to level 6 we had like a consistent selection time, where level 6 was worse for around 300 milliseconds. And we've seen that people really started, when they were like in level 6, they really started thinking more adjusting their hand and really like trying to think about more where could it be the control that they're trying to select. In study 2, we investigated the participant's ability to maintain the visuospatial memory while performing multiple selection while the drawer was left open. Before that, they always opened it after each selection, reopened it, and now the drawer was just opened once, and then they needed to perform multiple selections. We also compared that performance in when we had the imaginary drawer, or if we represented like a graphical representation of it, and then we had like this sphere which was then showing where our hand is relative to the squares which represented controls. And yeah, we found out that the graphical representation of drawer was, of course, much more accurate than our imaginary interface, but the interesting thing was exactly this: when and when not. So we found that if we compare the accuracy in each level, we see that in level 3 they both performed with the same amount of accuracy, so there was not much a big difference. But after that, we see that the imaginary condition starts going down, and that the memory retention starts negatively affecting the accuracy. This made also the drawer somehow to the sweet spot that we see that in level 3 we have really comparable interaction going on as if we have a graphical user interface. To understand the effect of memory retention, we also compared the data from study 1 to the results, to these results. And we see that really, indeed, having a fresh memory, as the gray line indicates, we have a much higher accuracy as if you don't have it, so it's really in the middle. And we found that there is actually no significant difference between graphical and imaginary when it's always reopened. and that if before only level 3 was comparable, in that case we would also have a comparable way of imaginary interaction in level 4. So we could say that, okay, it really depends how much time passed from the opening action and how good we will now interact. And if we practical, this means if we are planning longer interaction cycles, we need to start thinking how we would refresh the imaginary, the memory that we have from the opening action, or in how could we provide feedback. In general, we found that imaginary interaction is faster than graphical. In average, as mentioned before already, with this 300 milliseconds. And now back to the sweet spot that we see that if in any case how much time passed from the opening action till we can see that to level 3 or level 1 or level 2, level 3, we are as accurate as a graphical interface, but simultaneously we are also faster as the graphical interface. So that's really, really nice. In the last study, we investigated control revisitation. So this is important now for the spatial manipulations that we planned. And we asked if a participant now selects the control and he moves his hand away because he's like manipulating the parameter, can he find a way back to the initial point of the control? And we tested that by testing some one-dimensional placement tasks by two-dimensional and three-dimensional. And the participants had like now on the display these two cubes, a placement and a target cube, and they just need to align them based on the degrees of freedom that were offered. So what we found here was that higher dimension placement tasks, we didn't find here that the higher dimension placement tasks would negatively affect the revisitation accuracy. So practically this means that if we would limit the number of a control, for example, okay, let's say a one-dimensional slider is better than having panning or something like that, that would not have an effect on the revisitation. So in all the cases, in all degrees of freedom, participants came back to the control with an average accuracy around 70%. We also didn't find no clue that a movement to certain directions, for example, right or left, down, in all those conditions would perform worse or better. In terms of time, we see that the placement task was easier in one dimension, which was basically somehow related to the length of movement need to be done. But interesting, the revisitation time didn't follow the same trend, where we see that one-dimensional movement was significantly different to three-dimensional, but the pairs in between were not that significantly different. Yeah, then in the demo upstairs, we showed some applications. I don't know if you saw them, but there we had a navigation pin application. Maybe it's interesting to see, where we have basically three controls, and then we can position two pins in a two-dimensional, 2 degrees of freedom manner on a map, and then in between we can use like let's say a slider where we can then find a route between them. Or for example, where we have let's say a street view application, and we have two controls, where one control represents like a timeline where we can travel into the future, and oopsie. And the second control represents a panning tool where we can then look around in this view. And the last one was with 4 controls, which should represent like a global home menu of a car. And here you can see that we have each control representing like a common function. And for example, we can then control volume and the next track or previous track, or temperature, or ventilation intensity, or the seat into to access or turn off or turn on lights, which is basically like a 0 degrees of freedom. Yeah.
So
Let's.
And do we have some questions? Thank you very much for your presentation. I think this is very interesting work. I'm wondering whether or not this, I'm questioning why do you need this opening gesture? Could you have some fixed spaces in front of you? You have the space split into some sections and then just access each one from your memory. Maybe users can get used to.
Mm-hmm.
My radio is here, my air conditioner is there. I'm trying to understand why do you need to open the drawers so you can define how many.
Yeah, so the opening drawer has had like, the main idea was to first to have it, to do it wherever you want. So if we would say we have now here, let's say a physical object, whatever it is, and around
it's
it.
obstructing you, so you need.
Yeah, so then we would always need to grab there, and the benefit of this opening drawer is that I can do it here, or even if I'm standing a bit to here, I can still somehow use it. And also with the scale, because with the scale we just change the size of the controls, which is then nice for people that are much experts to have it on a smaller quick scale, and someone who started using it can open like a big drawer, and they really has like a 1 or 2 liter controls where they can then have a much higher accuracy.
Okay. Yeah.
But in reference to that, we could now think how we could combine it, for example, with physical or even graphical somehow representation or landmarks in the environment to maybe help. Yeah.
Thank you very much.
Yep.
Have you done any work on finding out what the concentration level of the driver would be when interacting with a 3D spatial interface rather than a 2D one?
Mm-hmm. We didn't investigate that. Usually we do that with some driver distraction test, but in that case we didn't do that. In a case, but it's definitely interesting, yeah, to see. It was more like, okay, let's try to find something which could potentially work really good because of the eyes-free and those benefits from imaginary interaction, which could theoretically work good for manual and autonomous. But a good next step would be what are actually now the limits if we are truly driver distracted or in certain special cases.
Okay, thanks.